Training a ranker is the easy part. Shipping consistent features online is where most LTR projects break. I will build the logging and scoring pipeline with LightGBM in Python. This is the pattern you'll be able to implement by the end, which logs features for parity checking and serves an online ranking with a latency signal and drift guard. I'm Professor Pi, teaching search and IR with simple Python. Most teams train a model and then wonder why online results drift. The model is fine. The features are not. In practice, small differences between the training feature pipeline and the serving pipeline cause ranking shifts, bugs, and slow incidents. Success means the same numbers are computed offline and at serve time, and we can score candidates within our latency budget while recording enough signals to debug problems. At a high level, feature logging gives you a contract. You log the feature vectors used to train the model and keep a compact record keyed by query and document. Online scoring recomputes those same features on the fly and uses the trained LightGBM booster to pick a top candidate. If the numbers match, you lowered your deployment risk. If they differ, you fail fast and fix the contract. We will build a tiny end-to-end demo that shows the idea. It creates a few queries and documents, computes 3 simple features, trains a LightGBM ranker, checks parity between offline and online feature code, and then serves a single query with timing and an auditable score. The pieces are small and realistic, so you can scale the pattern to a larger system. Now we will create a tiny labeled dataset and capture the exact feature vectors used for training. This snippet creates a tiny query document set and logs consistent offline features for each labeled pair. The dictionary queries max IDs to short texts, and docs holds candidate documents. The labels dictionary encodes graded relevance for training later. The function makeFeatures returns 3 interpretable features: token overlap, normalized by unique query terms, document length in tokens, and absolute length difference. The dictionary log collects these vectors, keyed by QID, docID, so they can be replayed and audited. The list feat names records column order to protect consistency across training and serving. The printed count confirms we captured all labeled pairs needed for the next steps. Next, we will turn the logged features into a LightGBM training dataset and fit a ranker. This code turns the logged features into a LightGBM ranking dataset and trains a LambdaRank booster. The list order fixes a deterministic sequence of QID, docket keys, so features X and labels Y align. The list groups counts how many pairs belong to each query, which LightGBM uses to compute ranking gradients. The LightGBM dataset packages arrays with group info, and the training call fits a small model using the LambdaRank objective, which optimizes pairwise ordering, and MDCG, which is a ranking quality metric. The variable iters reads the number of boosting rounds completed from the booster current iteration. Increasing num boost round, or num leaves, usually improves fit, but risks overfitting and slows scoring. The printed tree count confirms the model trained successfully. Now we will run a simple offline ranking check to see what the model learned. This example evaluates the trained LightGBM booster offline by ranking one query and contrasting it with a naive baseline. The list KS selects all QID, docID pairs for Q2 in the original order. The list XQ holds their feature vectors, and the booster predicts call returns model scores for those candidates. The variable top LGB chooses the document with the highest LightGBM score, while top base picks the one with the largest raw overlap feature, simulating a lexical-only ranker. If learning succeeded, The boosted model can prefer a more relevant document even when token overlap is weak. The printed comparison reveals how the learned reranker changes the top result. Next, we will add a parity check that recomputes features using the serving code path. This snippet verifies feature parity by recomputing features with an online save function and diffing them against the offline log. The function makeFeaturesOnline lowercases and tokenizes query and document text, then returns the same 3 features as training. The variable drift counts how many QID, docID pairs produce a different vector than what was logged. Matching outputs mean the serving code path mirrors the training path, reducing drift risk. If you remove lowercasing or change token rules, mismatches will rise immediately, signaling a contract break. The printed mismatch count confirms parity, which is a prerequisite for safe deployment. Finally, we will score candidates online using the verified feature contract and the trained booster. This code performs online scoring with LightGBM using the same feature contract verified in parity checks. The list cans enumerates the candidate documents to consider for query Q2. The list exo computes features on the fly via makeFeaturesOnline, ensuring order and values match training. The call booster predict returns per candidate scores, and the index with the maximum value identifies the best document. Printing both the chosen ID and a rounded score makes the decision auditable in logs. Increasing the candidate set improves recall but adds latency. Reducing num-boost round can speed scoring at some quality cost. The printed top result shows the final served ranking. In a real system, you map these pieces to your infra by storing the offline log in object storage, running parity checks as part of your CI pipeline, and emitting the chosen ID and score to your request logs for post-hoc analysis. Recap. What this is: a feature logging and online scoring pattern that enforces a contract between training and serving. When to use it: anytime you deploy learned re-rankers and need reproducible, debuggable decisions in production. One caveat: the parity check only catches feature mismatches, not label noise or training data drift. Next step: tune num leaves and num boost round to balance accuracy and latency while keeping the same feature contract. If short, practical IR helps, subscribe and watch the IR videos.